Welcome everyone to another OCP Top Call. This is call number 126. We have today Julian St. James from Meta and I think Mike Leah, and another person I forgot. Like, is it Dan?
Yeah, Dan Sobel
Yeah. Dan Sobel from TI, and I
from
have.
Precision OT, I should say, not TI.
Okay, perfect. Yeah, and I don't have the bios, so we'll skip the bios for today. And with no further ado, let's get the presentation going. So, Julian, Dan, and Mike, the floor is yours.
Okay, great.
Ahmed, this call is not on my calendar because we had call last week.
Yes, yes. I think something like got messed up, but just accept my apology, and we're gonna fix this.
Yeah,
Yes.
yeah, exactly.
All
I'm
right.
glad Dan reminded.
Yes, yes. Wonderful. All right.
Okay. Yeah, I guess I'll be lightly attended, but on YouTube, so it's fine. Yeah, so today I'll be presenting with some folks from Precision OT and myself about SFPs for RF over fiber. Something I learned from my last presentation was I should put a TLDR at the beginning. So to kind of give a high level overview of the whole presentation, for timing purposes, but for other purposes, you tend to use RF. For timing, RF comes in the form of GPS as your source of truth. Unless you are like a national lab or tied directly to a national lab, you're probably relying on some kind of satellite distribution for your source of truth of time. And distributing that over coax has severe limitations. The coax itself introduces a lot of loss. If you need to split it, you have to use lightning protected splitters and a bunch of other constraints. And so RF over fiber is used for a lot of GPS distributions, including inside of Meta, because it lets you have physical flexibility about the antenna. The antenna doesn't have to be, say, directly above your GPS server. You can put it where it's convenient on the roof, and then you can have a fiber that's small and flexible that you can run through your building and connect that to your end devices. And so the idea that I had was, well, SFPs are industry standard for electrical to optical conversion, and they should be used for RF purposes. There's nothing really so special about the SFP form factor that prevents that from being the case. So I figured why not do that? And so that's what I'll be presenting today. The diagram on the right is just a high level overview of the architecture inside of Meta for the PTP distribution. And as you can see at the top level, there's the time appliance open time server, which ultimately goes back to a satellite GPS distribution. So just to kind of go over that a little bit more detailed of what we're doing at Meta, this is all from public Meta blogs, so I'm not leaking anything or anything like that. But the current infrastructure has what are called Huber-Schuner, so that's the company, and they have GPS over fiber devices. So the antenna on the roof pictured there is powered over fiber. So there's a pretty high power laser going up to the antenna, which gives it power, which it then sends a signal laser back down with the GPS signal on it. And then there are devices that you put in the rack in the data center that convert the GPS from optical to electrical over coax SMA that you can then feed into a time card or other GPS receiver. And so some of the limitations of this architecture are that you can only use their antenna, right? You're getting a fiber from their antenna at a specific wavelength, whatever they're giving you, and you're limited to that architecture. You need their box at the bottom and you need their antenna on the roof, and they talk to each other, only to each other. It also limits the number of bands that you can support at the antenna, because if you want to have very good LNA that covers a wide frequency range, you're limited in terms of how much power the antenna can receive over a laser, because you have to supply a laser with power. So like a 1 watt or 2 watt laser, it gets converted to electrical to power the electronics on the antenna, and then also power a laser back down. So ultimately that puts some restrictions on how much you can do in the antenna. And also just kind of the general reason why I started thinking about this was that lasers fail. So if any laser gets damaged or fails in any of these devices, the antenna or the device in the rack, you have to replace the entire unit. There's no hot swappable laser. It's all just a fixed appliance basically. And that's kind of one of the reasons, at least my background is more on the transceiver testing field. That's why we have transceivers for the most part, is the flexibility, but also that lasers tend to fail faster than most other components in a data center or network system. And so these kind of architectures with these antennas don't have that kind of flexibility for replacement or upgrading or just being able to do something if it fails. And so this is, again, I'm not doing this as a Meta representative, so please nobody get angry about me if I didn't include your company here or anything like that. But I just was Googling around for, RF over fiber, not necessarily GPS over fiber, but just general purpose like RF over fiber. There's actually quite a few companies out there that make them. This is not comprehensive. I just kind of Googled it. This is what showed up. So like Optical Zonu has GPS and RF over fiber, RF optic. They have, different boxes. You can buy like very small standalone boxes, very ruggedized for outside boxes, anything like that. And rack mount and all these kind of things for different wavelengths, different kilometer reaches, different frequency bands, different amplifiers or filters inside, or power constraints, all of that kind of stuff. Some are managed, some are unmanaged, meaning you don't get any telemetry about the laser, or they have a console port, or they have management Ethernet interface. Basically, you can find kind of whatever. There's a bunch of different styles of these designs out there on the market. But just kind of looking at all of that, there does seem to be quite a large market. This was my interpretation. I was not in this field until I started working on the timing stuff, so I didn't know like, okay, where is RF over fiber actually used? But just looking at what the marketplace has in terms of products, there's things like TV over fiber, cellular over fiber, GPS over fiber is what we used. When I mentioned this idea to some people and they work in some quantum research or something like that, they mentioned there's use cases for just like clean sine waves. So like a single tone over fiber. You have a tone from some device or something and you need to get it to another that's physically not close to you. How do you get like a single tone cleanly over to a long distance? Um, and of course, there's probably other applications I don't know about. But all the current RF over fiber devices are either outdoor applications, so those have hardened cases and things like that, a lot of thermal protection, or like very fixed installs. So they're just like one RU boxes similar to the Huber-Schuner device where kind of the connections are fixed. You have, RF over coax connections, and then you have some integrated lasers with like LC connectors on the front panel. But none of these devices are designed for servicing the optical transceiver or changing it. So let's say you wanted to try just a cheap optic or like a LR, SR laser. You don't need a long reach, right? I mean, if you look at this one, there's one that supports up to 100 kilometers. So they're obviously using some pretty different lasers than something that only needs to go 1 kilometer. But then also if you wanted to say use a BiDi transceiver, let's say where you have different wavelengths over the same fiber, let's say you only have one fiber, but you need bidirectional transmission, there's no way for these devices to support that because everything is built into the box and all the transceivers are built in. You're paying basically for the laser as part of the appliance. And they're mostly designed for one-way directional links. So usually antenna or RF electrical to optical and then electrical back out. So there's not really a way with these boxes to kind of do like a bidirectional, some of the timing applications like White Rabbit or some of these more quantum applications, they need some kind of bidirectional link where you're sending RF both ways. Or for instance, with a like Wi-Fi over fiber, you would need a bidirectional link. It's not just like a GPS antenna down to your device. So a lot of these devices also don't have that kind of thing. The same thing for like TV over fiber. It's kind of one directional. So everything is kind of like purpose built in the RF over fiber market was my impression. People can email me if you disagree or find other use cases that I don't know about. And so as a hardware engineer, I was thinking, okay, well, if I wanted to build my own RF over fiber device, what are the kind of components that go into that, right? The RF input is relatively simple, right? It's just a coax, SMA, BNC, whatever kind of connector you want. I put some pictures here just to show that, it's cheap, like SMA connector is like $2 or something, or, panel mount is like a couple bucks. So, okay, so you're not limited on how do you get your RF into your box. And then if you want to have a filter or amplifier based on your frequency, say like a GPS LNA or a Wi-Fi LNA or a SAW filter or any kind of bandpass filter, these are also relatively cheap, relatively common. Just looking at DigiKey, if you search for RF filter, there's like over 3,000 different filters for different frequency ranges. 2.4, 1 gigahertz, GPS, cellular, whatever. So the actual components that you need to like take just a raw signal in and filter it and amplify it in the range that you want to design for is also not really that difficult to build in terms of components. But then the last tricky part is, okay, you have your filtered amplified RF signal and you want to convert it to optical. That's the part that I could not find any kind of device that as a building block existed today. So you can buy like, if you work with a vendor, a lot of vendors, they can sell you like TOSAs or ROSAs, which are the transmitter or receiver sub-assemblies inside of an SFP. But they'll usually ask you like why and how much, and it's not like you can just go to DigiKey and buy it. You have to go to a vendor and say, okay, give me some 850 nanometer ROSAs or TOSAs or something, and then you need to like build a whole system. They're usually like flex PCB mounted, so it's like you have to hand solder them onto the board. So there's not really like a linear electrical to optical, optical to electrical kind of building block that's standard in the industry for RF applications. And by linear, I mean really linear, where it has a very flat frequency response, or at least a smooth frequency response. Most SFPs are for digital applications, not for linear or RF applications. So the problem I saw was, okay, I can build the whole RF system, but I need something to do this electrical to optical conversion. And so again, I kind of alluded to this, is what are SFPs? So these are kind of like the industry standard for at least data communications. I know there's a lot of other form factors than SFP, QSFP, DD, OSFP, all these other form factors. But for kind of general purpose, small form factor optics, SFPs are the industry standard today. And so why are they used? Well, they're hot pluggable. So if your laser is damaged or dies, you can just pull it out, replace it. Very commonly done in the data center. At Meta data centers, transceivers like SFPs are basically treated as commodities. So they're bought in large quantities, replaced all the time. And if you want to upgrade them, so if you want to use a different kind of fiber or a different kind of fiber length, so you want to go from 1 kilometer to 100 kilometer, you don't need to change your box, your host, you just need to change your transceiver, because the laser is usually what is dominating the ability to go long reach or different fiber types, multi-mode, single mode, or whatever. And there's a very well-defined industry standard for these transceivers. So how to read from them, basically temperature, power, optical power, transmit, receive optical power. How do you turn them off? How do you turn them on? How much power do they need? Can you read back their serial number, vendor, all of this kind of stuff that you would want in a device that you want to monitor is all very well standardized in the SFP architecture ecosystem. And so for all data applications, these are what are used for connectivity and very well understood. But I wanted to, the whole point of the talk is about RF, right? Well, you want to do RF with an SFP. How do you do that? Well, doesn't exist basically. So I had to approach a bunch of different vendors, optics vendors. I was originally asking for transceivers, but I was telling them, okay, or I was asking for like TOSA ROSAs or something like that, but I was also approaching with the idea of like, well, the ideal case is a SFP that it works like a normal SFP. You know the pinout of the gold finger, like shown here. It has a, EEPROM for temperature and all that kind of stuff. And it just has a very linear conversion response. So from electrical to optical side and back has a very flat frequency response. Unlike most SFPs today, if you were to crack them open, which I've done, and you look at the chipsets that they use, they're typically like digital chipsets. They're trying to make some kind of 0 or 1 out of whatever differential signal you send into them. Whereas what is needed for this is a very linear, like you feed a signal in, it gets converted to optical and back with basically like some insertion loss, but is very flat frequency response. It's not trying to do any kind of digital approximation. And so I approached a bunch of vendors, but Precision Optical, with some of the guys here, Dan and Mike and another guy who wasn't able to join, they actually took the idea and made a prototype for me. I originally was not expecting that. I didn't offer them any money or anything, so I really appreciate that they made all that for me, because otherwise this talk wouldn't have happened. But basically they made this SFP prototype that's pictured there, and it has a pretty flat frequency response up to about 7 gigahertz. Obviously it has some insertion loss. I didn't ask for amplifiers or anything. I would rather not put amplifiers in the SFP because then that will limit the frequency range and everything that you're trying to do. But you can get with this prototype a flat, relatively flat frequency response with some insertion loss up to about 7 gigahertz. Again, with just a normal, I believe it's a LR laser because it's 1310, 10 kilometer. And so that has all of the kind of components in it to do that optical to electrical, electrical to optical conversion that I needed to build like fully open source, or at least open source if you don't consider the transceiver RF over fiber solution. And so this is what one of my initial measurements. Obviously, this graph is from their data sheet, so I wanted to just verify it for myself and see it work, basically. And I also wanted to do some experiments. So my first experiment, this is in the timing lab at Meta. I have on the left side is the SFP breakout board, and then I have a VNA here that's injecting a differential signal in and getting a differential signal out. And I think this scale is a little wrong. I think this might be the wrong picture, but basically I was able to verify their measurements where it has a relatively flat frequency response from the electrical to optical and back to electrical domain. So it looked good to me. I just had a simple fiber loop back on there. And the other part I wanted to measure was what happens if you have optical attenuation? How does that manifest into the electrical RF domain? So I added some optical attenuators here, and basically I saw a linear response. So if you have the VNA is configured to inject a 0 dBm signal, it then goes through the optical path, comes back, it's say minus 6 dB. If I put 10 dB attenuation on the optical side, so I'm not touching anything on the RF, but I attenuate the optical side 10 dB, that 10 dB shows up linearly on the output RF. So it's basically a one-to-one trade-off of optical loss for RF loss. So that's what the kind of golden standard is in coax world, is you are talking about how much loss are you getting per, say, per meter. But the loss per meter for coax is like exponentially higher than for fiber. So this kind of trade-off is exactly what I wanted to see. I didn't want to see some kind of distortion or something happen when I attenuate the optical side. I wanted it to pass through to the RF side. Because at least then it's like a very linear system. You don't have to worry about some kind of weird second order effects. So this experiment proved exactly what I wanted to see with these initial prototype transceivers. And I'm, of course, if you've seen any of my other talks, I love making prototype boards. So one of the parts of this was I wanted to design a PCIe card that could be a host for these type of SFPs. These SFPs didn't exist before Precision Optics made them for me. So obviously there's no host, quote unquote, to support them natively. So I made this PCIe card to expose basically 3 SFP ports to different antenna paths. So if you see on the right side, there's 6 SMAs. One is for the transmit path and one is for the receive path. Each path is designed with amplifiers or filters for a different frequency range. The top one, I think, is the 2.4. So I was trying to do like, if I wanted to investigate, like, say, Wi-Fi or something over fiber. The middle one is for like a sub-gigahertz path, just kind of generic sub-gigahertz is used for like IoT radios, something like that. So I wanted to put that on there. And then the bottom one is the one that's most of interest for the timing community, is like a GPS path. So this has GPS LNAs and also filters. And then I, just to have some kind of PCIe bridge, I put a I225 on there, and then I use 2 pins from that to do I2C to control a GPIO expander. So that's for things like selecting which amplifier you want to use, or controlling the RF switches on the board. And this design was fully open source. There's not really that much on the board. The backside is basically empty. It's pretty much just these RF paths and then a power supply for the SFPs, and then this kind of like I2C, I225 stuff. And so then I was trying to experiment to see, okay, I have this host board, I have these SFPs that do RF over fiber. Now I want to see GPS over fiber actually work with this board that I made. So maybe it's not perfect, but I want to see if it works. So I have RCB that we designed for the Neo M9N. So the RCB form factor is what we use on the time card. This is a M9N on the backside. I didn't take a picture, but you can just trust me on that one. And then the bottom side is like a RCB to USB breakout board that NetTime Logic made. And so I was able to, monitor the serial port of the Neo M9N. So this initial reference picture is just me connecting the antenna directly out my window or like by my door. And the Neo M9N has the 3D fix. It knows where I am. I'm sure if you look up this latitude, longitude, you can figure out where I live. But this is kind of like the baseline working GPS device. So just to prove that like my GPS receiver works. So then my home setup is quite messy. I have a lot of drawers and stuff, but my initial setup was, okay, I have my antenna in the window, the same antenna I used in this picture. I connect it to the input of this bottom SFP, which is the GPS path. It goes through that, then it goes through just a simple fiber loop back here, and then it comes back and it goes out from the other SMA to the Neo M9N. And so when I initially did that and I didn't have any LNAs enabled, so this is just a straight path, just goes from coax in to the SFP, optical back, coax out to the Neo M9N. It was, it got some lock, but you can see the signal level is quite worse. Again, this wasn't like a different day. This was like literally a couple minutes later. So it's not like it got cloudy and messed up all the GPS signal, but it was previously good. It had a good lock on a lot of satellites, 3D lock, and accuracy is like 1.1 or something. And then here, it still got 3D lock, still knows where it is, but the signal level is quite low. It doesn't see as many satellites, all that stuff. So, okay, at least I get it working. Maybe it's not as good as I want performance-wise, but it's still there. But I wanted to see, okay, well, I put all these LNAs on the board for both sides going into the SFP and coming out of the SFP. What happens if I enable them? And so if I enable the TX, what I call the TX LNA, so this is the LNA before it goes into the SFP. So you have your GPS antenna through the SMA, and then I enable the LNA on the board, and then it goes into the SFP TX path, then it's back to strong signal quality. So it's fully operational GPS over fiber through these linear SFPs. I get 3D fix, good accuracy, similar number of satellites I saw as before, and everything's working. So the GPS worked exactly how it should have. So that's kind of my takeaway today. I didn't have a whole lot of other topics other than that. I was mainly interested in showing that RF over fiber has a lot of application spaces, but it's also important for timing applications. We may not think of it, but GPS is a RF signal. It's coming from a satellite over the air. So any kind of RF over fiber solution can also play in the GPS or timing space. And if you use SFPs and cheap RF components, you can use this kind of SFP as a building block to design a very flexible or open source, fully end-to-end GPS over fiber solution or RF over fiber solution, whatever that application might look like, with all of the kind of benefits that you get from using a standard technology like SFPs. You don't need to think about like, okay, how do I monitor the SFP, or if other vendors start to build RF SFPs, how will they interop or anything like that. It's all very well defined in terms of, wavelengths that lasers use, what reaches, what kind of monitoring you can get out of the transceivers. That's all very straightforward and well defined in the industry. And so I just wanted to, again, shout out again to Howard and Dan and Mike from the Precision Optical Technologies team, because they took my idea, which was just an idea for me, and actually made me real prototypes out of, it could have just been a bare board or something, but an actual SFP, proper enclosure, working laser, transceiver monitoring, everything. And otherwise there would be no RF SFPs, if that's the term, in the world. So basically this whole talk is because they were able to give me these prototypes and make this whole process work. So I'm hoping to see that, if anybody has any applications for RF over fiber, that, you can reach out to them. If you need their contact info, let me know, julianstj@meta.com. But Dan and them, I know I didn't put your emails on here, but I'm sure they'd be fine with anyone reaching out. And that's the whole talk. I don't know, Dan or Mike, if you want to add anything.
Sure, I'll just add just a little bit on the standardization behind this. So these are, as Julian explained, these are standard transceivers. Basically, there's with digital electronics removed. So it's kind of just a pass-through design of a current product that we offer. The standard that they meet is SFF-8472. So it still meets that standard even with the analog output, which pretty much means first, monitoring is implemented over I2C. So you can actually monitor what's going on with the signal strength, temperature. It does not have a receiver, so you can't, that's kind of been eliminated, but all transmit parameters are monitorable and as defined by that standard. And because it is a standard, we would easily be able to offer this in any variant that would be required, meaning a wavelength. If WDM were to be used, multiplexing, where if you had to, say put 40 different wavelengths on a single fiber, you could have, 40 analog signals going across, a data center or a building on one fiber. So it wouldn't, that'd probably be potentially an advantage where wavelength would be selectable by the end user or the customer. Distance, this particular part was an LR 10 kilometer. Probably applications where a shorter distance would be required, potentially applications where longer would be required. And it's a standard SFP plus is capable of, over 100 kilometers, subject to testing the analog transmission, but being a much shorter, much longer with different transceivers. So basically that kind of thing is all customizable within the 10 gig SFP standards, and we're able to do that on this part. And then the other thing, as I mentioned, there is no receiver. Julian, you had mentioned there may be applications where a receiver could potentially be required, and that's just a matter of adding in, the receive circuitry and, for a different potential application in the future.
You mean for monitoring or for which application?
Well, is there any reason you would have like bidirectional GPS or bidirectional analog that would be potentially a possibility? There are transceivers that do that today, just I don't know if it's for like a GPS environment or not.
Well, these transceivers are bidirectional, right? I mean, I went through them.
Right. They are.
Yeah.
I mean, technically, yes. So.
Yeah, I think that's fine. That's all I
Okay.
needed. Yeah. I wouldn't want to put too much. The point was I wouldn't want to put too much into the SFP, right? It's a building block to get you to play with the optical domain. And then once you get that kind of like building block, then you can put a lot onto the board side or the host side to do whatever you want to do. So I think this was perfect for what I was looking for. But yeah, this was something, yeah, I didn't mention, I guess I could have added was, yeah, when I talked to you guys about this, you said like the laser itself is a independent subsystem inside the transceiver, right? Like you said, you can put like a DWDM, CWDM, BiDi or whatever. So cool.
All right.
Thanks, Mike.
Yep.
Okay, I guess any questions? Yeah, feel free.
And what's the bandwidth? I see the channel is 1310, but I mean the frequency is 1310, but
The RF bandwidth is
no. The optical bandwidth, sorry.
Mike, this should just be a normal LR laser, right? So it shouldn't.
That's a 1 gig LR laser, correct?
Okay. Yeah, so theoretically you could plug it into existing fiber networks then.
Correct. So yeah, that's just basically it's all of our transceivers are for your standard, like call it telecom fiber networks. So running WDM, BiDi, 1310, 850 nanometer, it's all the same standard, commonly deployed fiber.
So I don't have to worry about the roll off.
Right, correct.
Cool. Yeah, I wasn't expecting this, Julian, so I don't really have any comments.
No problem.
To like think about think about this a little bit because I've been all around this. I've built transceivers and fiber and RF and GPS and all this stuff, but I've never put it on an analog waveform on fiber.
Yeah, it's like my beginning of the slides was kind of the same thing, right? Like people are doing RF over fiber or something, but it's not quite in like what I see in the data world, right? The data world, SFP transceivers, everybody knows you need to take optical to electrical and back, and you want to do it separately from all your electronics, and it needs to be hot swappable. But I didn't see that with the RF world for some reason. So that's why I wanted to do this.
How much, I mean, I can understand what this cost-wise would be, but what about the media converter that you probably need to have in the front end? How much do those
You mean
run?
this, the SFP?
Well, you probably have from GPS, RF, you have a media converter, right? That goes to fiber.
Yeah, that's just the SFP.
It's just here. So there's a SMA or a TNC or something in the very front.
Well, the board I built, yeah, it's just SMA and it goes directly into the SFP. Probably if you build a different board, you would want to do it a little differently than what I'm doing here. But yeah, you can pretty much just go. I was just going. I mean, there's a Balin because the differential on a SFP, but you have SMA single-ended through some amplifier through a Balin into the SFP. That's all I did. So the
Oh, yeah,
electronics is very simple.
makes sense. Yeah.
But Dan, I don't know if you want to quote a cost here on the call or not, but
I'd be happy to send you a quote over after the call, Bijan, but I don't want to quote a price over this recorded
Oh,
call
yeah,
here,
yeah. No,
if you don't mind.
I'm not asking you to do that. I was just thinking in terms of maybe budgetary or list pricing or whatever, because um I just, if I could understand like what's the scale of the cost, then I could understand like who would be interested.
So it would be roughly the price of a normal 1 gig LX plus a little extra since this is a small run rate item.
Okay,
So it would be around
Okay.
that same amount, if that gives you an idea.
that's a pretty good deal. Yeah. Thank you.
and the electronics is pretty simple. I mean, the board itself is all top layer routing, right? It's just RF. So the host board, whatever you design, once you have that SFP, is pretty straightforward. So the cost wise shouldn't be too high either.
And you said you put some filtering at the after the receiver, right? I mean,
I
after
didn't actually need it. I think on the GPS path I didn't put it, but on the
Oh,
other
sorry.
paths I did. Because I knew what I was injecting basically. But I guess if you're designing like a general purpose or something, you probably want to add some filtering after amplifying. So it depends on how much link budget you want to allocate loss to filter, amplify back.
Cool. Now I'm gonna go do this. Yeah, because my house, when they built it, they put fiber in the walls, but I can't put any more cables in the walls. I already have what I have. I have a conduit, and whatever fits in there is what I get. So I do have fiber bandwidth, so this could really work out well for me at home.
Oh yeah, you can put anything over it.
In fact, I could probably piggyback it off of if I wanted to, off of local broadband too, because they use different spectrum. Diplex it.
Mm-hmm. Any other questions for anyone?
And you didn't, when you were doing when you looked at the signal linearity, you didn't notice any like linearity issues or anything like that caused by group delay problems or
So this was kind of my measurements of the SFP itself. So it's not 100% flat, but I put the markers up to like different frequency ranges. I think some of these kind of stuff is due to my cabling has some non-ideal measurements, and the eval board itself is also not meant for RF applications. This is a, SFP eval board for digital SFPs.
yeah.
So obviously the frequency response is probably not, ideal, but up to like 2.4 gigahertz, this marker is pretty flat and pretty low insertion loss. Again, this says 15, but I did other measurements that it was more similar to this data sheet number. So, yeah, I guess I didn't take the full S parameter set, but at least the insertion loss was pretty straightforward. If that was your question, I might have.
Yeah. No, I'm just thinking about the graph. Yeah. Yeah, that was my question. In fact, I was just thinking about diversity and putting two antennas on the same fiber.
Yeah, I mean, no reason you couldn't, right? Or, I mean, if
They're not, if the
you get a,
antennas are not correlated, then I mean, everything is the way it was explained, there should be isolation, there shouldn't be an issue.
you mean the electrically put them on the same, or where?
Optically, yeah.
Oh, yeah. Well, you would want to use a different wavelength, right?
Yeah, that's what I was saying. As long as they're on different wavelengths and the antennas, GPS antennas themselves are not correlated, then this could be a new thing. This could actually help you do GPS antenna diversity.
Right. So that was one of the reasons I was looking at it for like the meta deployment was if you want to have diverse antennas and you also want them to be on different bands, you need some kind of transport mechanism that you can use all over the place. You don't want to have one transport device for L1 and a different one for L5 or something like
Right.
that. Yeah,
Right.
bomb options and skews and stuff. So, and all of that easily fits within this frequency response. I mean, none of it's above like 1.5 gigahertz ish. So it'd be straightforward.
Very cool.
Any other questions? I think we're good then.
I think Dan had a question he posted in the chat.
Oh, I wasn't checking the chat. Security or crosstalk related issues that need to be addressed. I mean, I would say it has the same security and crosstalk issues or crosstalk I wouldn't expect because it has the same, as long as you have wavelength separation, same as you would with a datacom, it would be fine. I don't think crosstalk, because this is like a 1 gigahertz signal modulated onto a whatever terahertz laser. So as long as you have the terahertz separation, you should be fine. But the security, I suppose you would have the same security issues as you do with just coax, right? If you have a splitter, you could split off the optical signal and kind of tap it, but you have those kind of problems with any kind of RF and particularly over the air. I mean, it's just broadcast. So I don't think there would be anything too special about this setup for those situations.
So now we need a tap card without RF connectors, just with fiber connectors.
Just SFP cages, yeah.
Yeah.
I could. Yeah, I mean, that's why I built this as just a standalone distribution card, but that would definitely be possible now. I would just have to think about what to put on it. I mean, this is limited by faceplate, right? PCIe faceplate is limited, but particularly if you were to build like an appliance or something, I was thinking of something similar to these kind of boxes, then you could have it look like almost a normal network switch with just a bunch of SFP ports and coax ports. But it would all be SFP over fiber ports. Yeah. Any other questions? Cool. Ahmad, I think we're good then.
All good?
Yeah.
All right.
Cool.
So
Thanks,
yeah.
everyone.
Thank you, everyone. Bye, everyone.
Appreciate it. Thanks. Great presentation.
Thank you.
Bye.
All right, bye.